Welcome to this video on the general concepts of conic sections. This is the first of a 4-video series. This video gives you the general idea of what a conic section is, or what they are, I should say, and videos 2, 3, and 4 give you the mathematical mechanics of how to graph the 3 or 4 different kinds of conic sections using algebra skills. So let's get into the general concept of what is a conic section. Well, the word conic here refers to cone, and section refers to a cross section. So imagine you were to take a cone and take cross sections at different angles. Well, it turns out depending on the angle of your cross section, you would get different shapes. You can see that a circle here would be a cross section that's essentially horizontal or perpendicular to the axis of the cone. Whereas to get an ellipse, which is one of the other 4 conic sections, you might take a cross section of a cone at a slight angle. Whereas to get a parabola, as you can see here in the diagram, another conic section, you would take a cross section parallel to one of the sides of the cone. A vertical cross section would give you part of a shape called a hyperbola. And these are what are known as the 4 basic conic sections. But for the purposes of algebra, we're going to be focusing on what conic sections are in regard to a more graphic situation where we're trying to graph things with x and y coordinates. But before we get into the how-to videos, which are the 2nd, 3rd, and 4th of this series, let's take a general look at what a definition of a conic section is algebraically, rather than just thinking of it as a cross-section of a cone. We'll start with a circle. A circle is a familiar shape to all of us, and it's defined essentially by a point and a number called a radius. So if I said, let's imagine all points that were 3 spaces away, for example, from this point, well, there would be lots of points that are 3 spaces away from that point. Here's a point that's 3 spaces away. Notice the distance here is 3. But here's another point that's 3 spaces away from the given specified point, or the center. But that point also would be on the circle. Well, here's another point that's 3 spaces away. It's 3 spaces away in a diagonal fashion, but 3 spaces away nonetheless. And if you think about it, there are infinitely many points which are 3 spaces away from this given point. Here's one that's 3 spaces away. Here's one. Here's one. Here's one. And here's one. And so what we have essentially is an infinite number of points, all of which meet the criteria 3 spaces away from the specific given point. And that, as we've always known, is a circle. In general, we obviously call this given point the center, and a circle is defined again as having the characteristic that any point would be on the circle if it's 3 spaces away from this given point. Now, while there isn't anything terribly complicated about that, let's look at another conic section called the ellipse. You may know this in a more informal language as just an oval shape of sorts. But an ellipse actually has a geometric or algebraic definition. An ellipse is defined by any 2 given points and a number. For example, I could define an ellipse by saying, here's 2 points and the number 5. Well, how does the number 5 define an ellipse? Well, it turns out for any point to be on this ellipse, notice the point at the top of the screen, you may see it in red. For a point to be on the ellipse, it must have the characteristic that those 2 distances add up to 5. Now you can see for this particular point, I calculated the distances away from the 2 given points. The sum of those 2 lengths is 5, and therefore that point is on the ellipse. There are other points that match that criteria as well, the criteria that the the sum of the two distances from the given points is 5. For example, this point here on the left side of your screen in red, if you compute its distance to each of the given points, 1 and 4, they too add up to 5, and therefore that point is also on the ellipse. But you can imagine that there would be infinitely many points that match this criteria. For example, each of these points is exactly 2.5 spaces away from the two given points. 2.5 plus 2.5 also adds up to 5. So there's another point on the ellipse. And if we could imagine finding all of the points that met this criteria, the sums of the distances from the two main points is 5, there'd be a lot more. Here's one, here's one, here's one, here's another one, and here's another one. And what I didn't show there, but what I calculated, is that if you were to take any one of these points, compute the two distances away from the given points, those two distances, while they would be different from point to point, would always add up to 5. If you were to do this infinitely many more times in theory, you would find an ellipse shape. And hence the definition of an ellipse is as described. These 2 points are called focal points, or foci, or each one of them is a focus, just to give you the name of the 2 given points. And again, if you're wondering what the definition of an ellipse is in an algebra geometry sense, it is all points whose 2 distances away from given points are always a constant number. In this particular example, we've chosen 5 as our constant number. And every point on this ellipse, regardless of where you choose it, has the property that a plus b, as shown in the diagram, would equal 5. Now let's take a look at the next conic section called a parabola. You may have heard of it in other algebraic contexts before. Let's take a new look at physically what a parabola is. A parabola is defined by one line and one point. You can put the point and line anywhere you like. Those 2 objects define a parabola. Here's how. What would it mean for a point to be on the parabola defined by that point and that line? Notice the red point in the upper right corner of the screen. That point turns out to be on the parabola. And here's the reason. If we compute the distance from that point to the given point, you see it in green as 5. And then we compute the distance from that point to the line in a perpendicular fashion, in other words, the straight distance to the line. Those 2 turn out to be the same. Now that point turns out to be on the parabola because those distances are the same. Here's another point on the parabola. Why? Because when you compute the distance to the line and then compute the distance to the given point, they're also the same. Now notice they're not 5 in this case, they're both 2, but they're the same distance. And that qualifies this point to be on the parabola defined by this given structure. Here's another point on the parabola. How did I know it was on the parabola? I computed the distance to the given point, and I computed the distance to the line, and they were both 3. They weren't the same as the previous ones, which were 2 and 5, but that doesn't matter. Any point which is equidistant from the given point and the line is on this parabola. And those 3 points aren't the only points that match that criteria. Here's one, and I didn't show my work, but the distances are the same. Here's another one, and here's another one. Probably the most important point on this parabola, here's another one by the way, is this one here. You may see it in green. It's the lowest point here. That point turns out to be, in this particular case, a half a space from the given point, or the black point, and also half a space away from the line. That point, as we'll see in a later video, is called the vertex or turning point of this parabola. But you can see 8 points that match this equidistant criteria. But those aren't the only 8. There's infinitely many of them. And if we found them all, we would have this shape. We call that shape a parabola. The line is called the directrix, and the given point is called the focus. In general, for a point to be on the parabola, the distance away from the focus and the distance away from the directrix must be the same number. All these points collectively make the parabola. And lastly, let's look at what a hyperbola is in its geometry algebra definition. A hyperbola is, again, like an ellipse defined by 2 points and a number. We're going to take that example number here to be 4. So suppose we said, here's 2 points and a number. Let's find the hyperbola that matches them. Let me explain. This point turns out to be on the hyperbola. What makes that point a valid point on the hyperbola? Well, when you compute the distance between that point in red and the 2 given points, then their difference is 4. Notice the green distance and the blue distance have a difference of 4. One is 4 spaces longer than the other. And because our special number in this particular hyperbola is 4, that point must be on the hyperbola. But that's not the only point for which the difference of the distances is 4. Here's another point. You'll notice the distances are 5 and 1, different from the last time, but 4 apart nonetheless. Therefore, that point is also on this hyperbola with our specified number of 4. Here's another point on the hyperbola. I computed the distance between that point and our 2 given points. The distances were 7 and 3. Those are also 4 apart. But those aren't the only 3 points on the hyperbola, of course. Here's another point. The difference of the distances being 4. Here's another such point, and another another one, and another one. And if we did this infinitely many times, which you can't actually do, but in theory, if you did this infinitely many times, you'd find all the points. Again, these 2 points are called foci, or each one is a focus in singular. And these focal points define our parabola along with the difference of 4, our example number in this case being 4. The general idea, once again, is that a point is going to be on the hyperbola if it matches the criteria that the difference between A and B is 1. Now, you're unlikely to ever have to perform tasks related to the information you just saw, but at least you now have a general sense of what the 4 conic sections are in a geometric graphing sense. Well, what is this video series about then? Well, in general, it turns out that if you were to have the graph of any conic section, circle, ellipse, parabola, or hyperbola, that it would be expressible in this general form that you see here, where A, B, C, D, and E represent actual numbers. You won't be given an A, the letters A, B, C, D, or E ever, but you'll have numbers in those places. For example, you may be asked at some point to graph this conic section. We may even see this later in the video series. But for now, before we get into the how-tos of the actual graphing of conic sections, which comes in the beginning of the next video, let's just pause and think a little bit deeper about what graphing means. So suppose we were asked to graph this equation. It's likely to be a conic section because of its format. And one thing that we could do to graph it is to plot points. I'm not suggesting this is a good strategy, but it gives us a general idea and reminds us what graphing is and shows a connection between what we know about graphing and the conic sections we'll be graphing in videos 2, 3, and 4. What if I wanted to know if there were any points on this graph that had an x-coordinate of 3? I'm not saying there are or aren't, but what if I wanted to investigate? Is there a point on this graph or multiple points that have 3 as an x-coordinate? If you're wondering why I chose 3, just a random number, just trying to find some points on this graph. No particular reason I chose 3 per se. But what I could do is I could plug 3 in for x. Now, I don't want to show all the messy algebra, but some of these terms were constant, and I was able to reduce this equation down to this. But look at that equation there. Isn't that something that you could solve using the quadratic formula? You may remember that from previous algebra classes. Well, I did the quadratic formula on scratch paper, and I got 2 answers for y, for this one particular given value of x. Well, what does this mean? This means if x is 3 and y is 5, the equation is satisfied. But it also means if x is 3 and y is -1, our equation is also satisfied. And if the 2 points, 3, 5, and 3, -1, both satisfy the equation, then by definition, they're both on the graph. I've just found 2 points on this conic section. What else do I know about it? Well, at this point, nothing. Now you might be asking yourself, is this how I'm going to graph conic sections? Am I going to pick random x's, plug them in, and find y's? No, it's a horribly inefficient method, but it's worth examining before we start video 2 of this series. Let's do this again with a different random, so-called random value for x. Let's look at what happens to y when x is 4. So I'm posing the question, is there a point on this graph that has an x-coordinate of 4? Well, maybe there is and maybe there isn't. The only way to know is to plug in 4 for x. Now, without really focusing on the algebra, which I did on scratch paper, I used the quadratic formula here. And you'll recall that the quadratic formula has a plus or minus symbol in it, and sometimes involves radicals, which I used a calculator to estimate the values of y here. Again, if you're wondering where I got those y values, they came from the quadratic formula and a calculator. But what does this mean? It means when x is 4, there are 2 different y values that can satisfy this equation. And there they are, the point 4, 4.6 on top, and 4, -0.6 on the bottom. And it seems as though anytime I plug in an x value, for this particular conic section anyways, that I get 2 y values. That needn't always be the case, but so far that has happened. If you're still wondering, is this how I graph conic sections? No, there are some amazing shortcuts that we haven't gotten to yet. But conceptually, this is important. What if I were to pick another so-called random value of x? If I plugged in 1, simplified the algebra, and used the quadratic formula, it turns out I would only get 1 answer here. You may recall from algebra that your quadratic equation has a single answer when the radicand, the thing under the radical, is 0. That's what happened here on my scratch paper. The important point is, I've discovered that when x is 1, y would have to be 2 for this equation to be satisfied. Looking at the graph, that means that it must pass through the point 1, 2. So in my journey to discover points on this conic section, I could keep doing this process, and watching me do the algebra is going to get boring. But I did the algebra when x equals 6 just to prove the point one more time. When x equals 6, I plugged in 6 for x, I used the quadratic formula, and I got a non-real answer. Notice the imaginary term here. You may recall from algebra that whenever your radical has a negative number under it, or the radicand is negative, you get non-real answers to your quadratic equation. But what does that mean graphically? Graphically, it means when x is 6, there is no real y value that satisfies this equation. And while there are 3-dimensional ways to graph complex numbers in this context, the tradition most of the time in graphing is this. If you get a non-real answer for a variable, you simply don't count that as a valid point on the graph of the equation. And so there are no viable points when x is 6 here. But what have we seen so far? We've seen that for certain x values, there are 2 corresponding y values. For certain x values, there's 1 corresponding y value. And for certain x values, there are no corresponding real y values that satisfy this equation. What if I were to continue this process over and over and over and over again? Eventually, I would have a general sense of what points satisfied this equation. And after doing this many times, I would have the supposition that I must have an ellipse here, and this does in fact turn out to be an ellipse. How would you know that? Well, a future video will give you more detail. But for now, the concept here is that if you were to plot enough points, you'd eventually know that you had an ellipse here. But this brings up a sort of problematic issue. First of all, plotting random points can take forever. There's a little bit of luck involved, too, in picking the right x's that are going to give you a decent picture of what the graph looks like. And I used a calculator to do most of those points. And we generally don't like to rely on luck. And as far as relying on a calculator goes, there's nothing wrong with that. But consider the following thing. Couldn't I just type this equation into an app and find out that this is an ellipse? That's what I absolutely could do. If you were just to go to, say, Desmos, which is just one maker of apps, and type in 9x squared plus 4y squared minus 54x minus 16y plus 61 equals 0, boom, this ellipse would pop up. So if we have apps that do this for us, why is there even any reason to bother doing it by hand without a calculator? Well, that's an interesting question. One thing is that it teaches us lots of mental processes, and our brains tend to grow as a result. So chances are you're in a math class, and if you're in my class, then this is definitely the case. But chances are that you're in a math class where you're required to, for example, graph this thing as an ellipse without a calculator. But wait a minute, I just graphed this thing as an ellipse with the use of a calculator. So how then are you expected to go about the process of doing it without one? Well, there are some amazing shortcuts that have been developed over the last 400 years, and those are what video 2, 3, and 4 are all about. And that concludes the first of 4 videos in this series.